We are slowly getting ready for the ACT, or SAT rather, as we've been going through this, and I've been trying to do a question of the day, so that's where we will start today's lesson at. So you can see what is the area of a circle. So we're looking for area of a circle in this case. Circumference of 12 pi. Now, if you don't know how to calculate the area of a circle, that's not a problem. There is, and I showed that to you in our actual SAT review day, they give you a formula sheet. And circumference of a circle, first of all, is calculated, and this is given on that formula sheet as 2 times pi times r, where r is the radius. And they also tell you how to calculate area. Area is just pi r squared. So to solve this problem, what we first have to do, circumference is 12 pi, so we can actually write an equation using this formula. I'm going to color that highlights this formula right here. And so we'd say, well, circumference is 12 pi, and that equals how you calculate circumference, which is the 2 pi r. And so 12 pi equals 2 pi r. If we solve this thing to figure out what r is, that would tell us the radius then of this particular circle. So I'm just going to divide here by 2 pi on both sides. On the right-hand side, 2 over 2 is 1, and pi over pi is 1, so I just have r. And on the left-hand side, I've got a 12 divided by 2, so that's 6. And then pi over pi is just 1. So I know the radius of this circle is 6, and now I can calculate what the question asked for, which is what's its area. Now that I know r is 6, oops, I put my squared there, so 36 pi would be our answer. Now on to new stuff. This is the last day of some of our rules or laws that we're talking about. Today we're shifting gears a little bit. As you can see, we're going to be talking about properties of radicals. Now remember, radicals and exponents are very, very closely related. So x to the 1/2, for example, is the same thing as the square root of x. And x to the 2/3, for example, is the cube root of an x squared. Terrible looking parentheses. So when we've been talking about all of these exponent rules, we've also been keeping in the back of our heads that hold that exponents are radicals. And so now we're going to be talking about some of the rules we can apply when we are working in radical form. We got the product property and the quotient property, just two properties we have to look at. Product property, you can see real simple. If you've got the nth root, so this could be a square root or cube root, a fourth root, fifth root, doesn't matter, some root of the product of two things, you can separate the radical. We've actually used this all the time. For example, when we would square root 8, for example, we would think of this as the square root of a 4 times 2. And then we could square root the 4, and we'd get 2 root 2. But what we're really doing is rewriting it as a root 4 times a root 2. That's this law right here. I had a product of things, a times b. I had 4 times 2. It's equal to the square root of 4 times the square root of 2. So I can separate that radical into the product of two separate radicals. And this gives me then 2 root 2. So we have used this idea before when we simplified. Let's look at a few examples. There at the very top, underneath the word examples, there's the formula again. This time, though, I can actually, if you notice, I can't take the cube root of 2. I can't take the cube root of 4. But if I have the product of two radicals, I can just write it as the product or the radical of the product. So I can rewrite this as the cube root of 2 times 4, which is the cube root of 8, which is actually 2. So by using this, how you multiply radicals together, we can get it into something we actually know the cube root of. Another example of this. In this case, we're going to work in reverse. We're trying to simplify this, so we just start factoring it. Let's see, I think it's divisible by 6. It's 6 times 48, so it's 6 times 18. Yeah. Let's see here, and that would be the cube root of 6 times 3 times 6, because that's what 18 is equal to. So it's the cube root of, my 6's are 2 times 3. There's a 3. This 6 is 2 times 3. And you'll see I've got 3 3's in here. So what this is equivalent to is 27. That's 3 times 3 times 3 times 4. And this now, this law up here allows us to break this up as the cube root of 27 times the cube root of 4, which is 3 cube root of 4. That's a long ways about going and doing this. As soon as I get to here, everybody, oops, didn't want to circle that 2. As soon as I get these 3 3's, I immediately pull a 3 out, and I'm left with the cube root of 4. But this, the reason we can do this shortcut is because of all of this reasoning over here. See, nope, that was it for that one. So multiplying radicals, easy to do. Dividing radicals, if we have a division of 2 radicals, like we do here, a radical divided by a radical, we can group those together underneath a single radical sign. Notice some of the particulars. These both have to be the same index. Okay, and that was true of our last one as well for multiplication. So let's look at this in action. So this problem right here, this would be kind of difficult to do. You would have to try to break down the root 80 and then see if you could simplify. But instead of doing it that way, we're going to apply this law up there, this property, and just say, well, this is the same thing as the square root of 80 over 5. And now if I just work inside the radicals, I can take 5 into 80. It goes in there 116 times. And so the answer is the 5th root of 16. Now I would try to break that 16 down, but I can see that's 8, that's 16. It's only made up of 4 2's, and I need to have 5 2's. So I can't take anything out of this, and I would be done right there. Another example of this quotient property, same idea. We're going to write this as a single radical. Now we're going to carry out the division inside the radical. That's 81. And 81 is 3 times 3 is 9 times 3 is 27 times 3 is 81. It is 4 3's, so it is just 3. The last thing we have to talk about is what's called rationalizing the denominator. And this only comes into play when we have division. Okay, so we have to have a denominator in order for us to have to worry about that. When we are in simplest form, when we're done with a problem, there's 2 qualities we want to look for. The first one, you cannot have any more perfect square roots inside the radical. Okay, so for example, when we have root 8, there is a perfect square root in here. That's the 4. You can't have that when you're in simplest form. After we've taken the square root of 4, now we are in simplest. So we can't have any other factors that we can square root or cube root, 4th root, depending on the type of problem we're doing. And the second one, which this rationalizing denominators is about, is you can no longer have radicals in the denominator. and that's why it's called rationalizing it. You're getting rid of the radical. So let's look at simplifying and making sure we meet these two qualifications when we've got the cube root here of 27x to the 9th. So there's a couple ways you can go about simplifying this problem. One way right away you could do is this is the cube root of 27 times the cube root of x to the 9th. The reason I broke it up like that is because I can cube root 27. It's 3 times 3 times 3, so the cube root is 3. And I can take this radical and think of it as being in exponent form. It's x to the exponent's 9 with a denominator of 3. And this is very useful because now this is 3 times x to the, well, 9 over 3 is just 3, so this simplifies to 3x cubed. That's one way to go about it. Another way you could look at solving or simplifying this problem. We could, I'm going to start right back here at the beginning again. Cube root of 27x to the 9th. You could have just started factoring and started going, well, 27 is 3 times 3 times 3. And when you do that x to the 9th, think about that for just a second. There's a group of 3 x's, so an x comes out. There's a group of 3 x's, and there's a group of 3 x's. X to the 9th is made up of 9 x's multiplied together. Now remember, when we're doing cube root, it's asking, what do you have 3 of a kind of? So we got 3 3's, so a 3 comes out. 3 x's, so an x comes out, an x comes out, and an x comes out. It's just a case of how many groups of 3 can you get that 9 into? You just have to take 9, divide it by the 3, it tells you get 3 groups. Regardless, you end up with the 3 comes out, an x comes out, then another x, then another x, so that's a total of 3x cubes. Just another way to look at the same problem. Next example. Looks really, really tough, but let's just break this down. These are all factors. And what's nice about when everything's a factor like this is you can just break these fractions up. This is the exact same problem. Remember how fractions multiply. When they multiply, it's just top times top and bottom times bottom. So as long as I've got, so this is really, if I were to remultiply it, I'd have 6 times x times y to the 3/4. And my denominator would be 3 times x to the half y to the half. But by breaking it up like this, boy, now these look like they're pretty doable. Look at that. That's just really 6 over 3. Here I've got common bases. And we have a rule for that. And the rule is keep the base, but take the exponents, take the numerator exponent, subtract the denominator's exponent. That's how we divide them. And then for our y's here, again, we got the common base. We do exactly the same thing. Y to the, and we do 3/4, the numerator's exponent minus a half, the denominator's exponent. Now the rest of it's just clean up. 2x to the 1 minus a half is a half. Y to the, now you may have to get out a calculator to do a little fraction math, but that's 3/4 minus 2/4. Okay, I just got a common denominator there. 2 over 4 is still a half. 3/4 minus 2/4 is 1/4. And that'd be as far as we could go. There's nothing we could take out of these radicals, even if we went into radical form. Last example here, number 13. Problem 13. Now this is the last one. I should put a star by this thing, because this one's really going to cause us some difficulties. The first thing I would do is I can separate these two. That's x to the 10th, and that's just a y to the 5th down there. Now I'm just doing square roots. That's going to be important. So the way you can think of this is how many groups of 2 can I get in x to the 10th? Let's switch to exponential form, and maybe you'll see that when we do it that way. What we have here is just 10 over 2, so that's just x to the 5th. In the denominator, we have y equals 5 to the 5 over 2 power. You can, I'm trying to think of the best way to think of this. This is the same as y to the second plus y to the half. Because this is equal to 2.5, so that's y squared, now y to the 0.5. And that's important because this means this is equal to x to the 5th over a y squared root y. I've written that denominator with a radical in it on purpose. One of our conditions is we cannot have a square root in the denominator. And so you're going to have to learn a little trick, which is to multiply by whatever number would make the denominator a perfect square. In this case, I've chosen root y. And I've chosen root y because in the denominator, that would give me the square root of, I have a y to the first times a y to the first. That's a square root of a y squared. And I can now square root y squared. The square root of y squared is just y. So I end up with x to the 5th root y all over y to the, I already had 3, but out came in another y. So I got y to the 4th. And that would be our simplest radical form. Now, I know these things are tough. I'm going to start a few of the homework problems to help you get up and running. That's our last one. And we won't do the easy ones. I think 1 you should have no problem with. Just start factoring it. Number 2, the same thing. Start factoring it. Let's take a look at number 3. 3 would be one that would cause us difficulty. Okay. Even if I put 3, if I put 5 and 4 underneath the same radical, if I do this with it, cube root of 5/4 like that, that doesn't help me a whole lot because I can't simplify these two. Okay, so no simplifying goes on. So really the only thing I have to see is if I can take anything out. I can't take anything out of this cube root of 5, and I can't take anything out of this cube root of 4. But now I have another problem. The second condition is I can't have a radical in the denominator. So I have to fix it. We fix it like so. I have to take it times the cube root. It's mandatory. That's the only way we can multiply radicals if they're both the same type, cube roots or 4th roots, whatever. Okay? And I want to make sure whatever I multiply by makes the denominator a perfect cube. And so if I think about this force for a second, the 4 is made up of a 2 times 2. If there was one more 2, I'd have 3 of a kind. And so that's what I multiply by. I put in one more 2. Now in the numerator, we're using the law for multiplying underneath radicals. You just multiply the stuff underneath the radical. And then down below, I multiply the stuff under the radical, but I rigged it so it would be an 8. Why 8? Because the cube root of 8 is just, cube root of 8, should be my 10 right here. The cube root of 8 is just 2. It's 2 times 2 times 2. And that is our simplest radical form. So we had to do that because we wanted a perfect cube down here. And 4 was not a perfect cube. But now we've got our radical expression in perfect simplified form. I can't cube root any of the factors of 10, and there's no radical in the denominator. See, I think number 3, you're going to have to do a little game like that too. Number 3, when you're starting that, I would separate it right away and just focus on how can you get rid of that root 8 in the denominator. 6, you're going to have to work to get rid of that cube root of 4 in the denominator. Same with 7 and 8. Let me do one more of these for you. Let's do let's finish 5. 5 is kind of a curious one because I could do a multiplication right now and I could get rid of that root 8. But instead what I'm going to do is what I think everybody should do first is I'm going to simplify root 8 because I know root 8 is 3 2's. One pair of 2's comes out and I'm left with the 2 inside. So I would simplify it first, and now I just have to get rid of a root 2. Well, to make a root 2 into a perfect square, I just multiply it by itself. On top, that gives me a root 6. On the bottom, though, it gives me a 2 times the square root of, we multiply inside times inside, 4. So that's root 6 over square root of 4 is 2, root 6 over 4. Now I've shown every single step there. Some of these we can do in our head. But that does show you every single step to get down to the ultimate answer. That should get you through your homework, I hope. Make sure you come to class, though, and we can get some better guidance.